So now we want to look at non-parametric regression. Let's look at an example here, for example. So this figure right here shows a different example for regression. So the simplest model you can do is, I guess, to just connect the dots, okay, which we call piecewise linear regression, okay, which is chart A here. Obviously, as you can see, this is a very overfitting the data by just passing through the points, and probably will not, might not generalize very well to new data points. So this model right here creates a function h of x that, when given a point, a query xq, it will essentially consider the training examples. So if I want to make a prediction at x equal 3, for example, it's going to just look at the one on the left, which is x equal 2, and then the one on the right, which is x equal 4, and give me the middle value here as the best guess for x equals 3. Okay, so just a pure interpolation between 2 points, one lower and one higher than specific data point I'm looking for. Now, obviously, if you're looking for anywhere outside this range, say x equal 15, you won't be able to get a prediction using this model. When noise is low, this simple method is actually not too bad, okay, which is why it's very popular in spreadsheets and other charting software. But when the data is noisy, the resulting function is spiky and does not generalize well. Now, k nearest neighbors regression improves on this simple model, the connect the dots model. Instead of using just the two examples, one to the left and one to the right, of the query point xq, we're going to use k nearest neighbor. Okay, so for example, in this chart, we're going to be using k equals 3. A larger value of k tends to smooth out the magnitude of the spikes, obviously, and although the resulting function has some discontinuities. Okay, so you can see here in chart B, we used k equals 3, so we used the 3 nearest neighbors, and we just took the average value of the 3 neighbors, and we're going to use this value as a prediction for any point that falls in this range, and then and so on. So you can see that it's going to give us a different set of predictions than the simple connect the dot approach. So h of x in that case is the mean value or the average of the k points. So we just sum y and divide by k. So notice that at the outlying points near x equals 0 and x equals 14, the estimates are poor, just because all the evidence comes from one side and ignores the trend. Okay, so it has the same weakness as the previous model in dealing with the edges. Now in chart C, we did k nearest neighbor linear regression, which finds the best line through the k examples. So here, for example, for this piece, we used these 3 points, and we fit the best line between them. And then we take the next 3 best neighbors, and we fit the best line, and so on. So that's, instead of just taking the average of the 3 points, we try to fit a line through them. So this does a better job of capturing trends at the outliers, but it's still discontinuous, as you can see. Okay, and we still don't really know if k equals 3 is the best option here, or is there a better way to find k. So k, as you can tell, this model depends on two key features. First one is your distance measure. You have to correct the right distance measure. And number two is how many neighbors you use in making your prediction. Now, if you look at figure D, we did what we called a locally weighted regression, okay, which gives us the advantages of nearest neighbor, but as you can see, no discontinuity in that case. Okay. So to avoid discontinuities here in h of x, we need to avoid discontinuities in the set of example we used to estimate h of x. So the idea of locally weighted regression is that at each query point xq, the examples that are close to xq are weighted heavily, and the examples that are far away are weighted less heavily, and the furthest not at all. So the decrease in weight over distance is typically gradual and not sudden. Now, how do we determine how much weight do we give each data point? We use a special function that we call a kernel, whose input is the distance between the query point and that specific data point. So a kernel is another word for a mapping function. Okay, so a kernel function k is, in this case, will be a decreasing function of distance. The maximum possible weight will be if you find a point at distance 0 from your query point. And then the further away you go, then the lower the kernel will be. So this way, the closer the points is to a query point xq, the higher the weight. Okay. The integral of the kernel value over the entire input space for x must be finite. Okay, so if you take integration of the kernel function over the entire input space, you can't be getting infinity. So this guarantees that the weights are continuous. Okay. If we choose actually to make the integration result equal to 1, then in that case the calculations will be much easier, because you're essentially forcing the sum of the weights to be 1. Okay, so they're already normalized, so you don't have to worry about normalizing them later. So for example, to generate this figure D, they use the kernel, which is the max function that is max of 0, so the kernel has to be of course maximum of 0, and 1 minus 2d over w squared, with the kernel width w equal to 10. Now you can use different shapes, different functions for kernels. I mean, there are a lot of people who published different kernels. A very famous one is a Gaussian kernel that's used also. So typically the width of the kernel determines how far away from the query point you're going to consider. Okay, so the wider the kernel function, this means that you're going to give even a small weight to points that are very far away from your query points. Now, doing locally weighted regression with kernels then becomes straightforward, because for any query point xq, we solve the following weighted regression problem you can see here. So as you can see, this is our regular problem we talked about last time, except now we multiply each data point, each error by how far, by the kernel of the 2 points xq, which is a query point, and xj. So note that we need to solve a new regression problem for every query point. Okay, that's why it's called local, right? So now the only positive then from this process is that each regression problem, each local regression problem is actually very simple because you're only considering few points, okay, which are essentially the data points that are within the kernel width. Okay, so if you feel that you're doing too many function evaluations, then you can reduce the width of your kernel and still keep the advantage of obtaining a nice continuous function. So this method actually, so when we apply this method, you can see here in graph D, this has a kernel width of 10, so which means that to get the equation at point 0 here, we used everything all the way up to 10. So we used all this data to get the equation of the regression line around point 0, and so on. Okay, the next non-parametric method we want to talk about is support vector machines, which is a powerful method for machine learning and classification. It was very popular in the early 2000s, before deep learning and neural networks and so on, because it's essentially it's an off-the-shelf supervised learning approach when you don't know much about the domain that you're classifying in. So let's stop this section here and continue in the next section.